10.8 billion years ago, there was an event so extraordinary that without it, nothing would exist. It was the beginning of our universe, a time when an enormous amount of energy in an infinitely small space violently expanded, creating our universe and everything that we see around us today. It is perhaps our greatest scientific achievement to understand the history and nature of our universe. But there is a problem. The theory doesn't explain where the universe came from. So what caused this remarkable event? What caused everything that we see around us to exist? And why is there something rather than nothing? We asked 6 scientists at the University of New South Wales, specializing in various fields of physics such as astronomy, theoretical physics, particle physics, cosmology and astrophysics, what they think happened before the Big Bang.
Before the Big Bang, it's an interesting question because that's...
I'll just repeat, there's no data to base anything on, right? It's an open question at present.
Oh dear, that's a really big question. Well, I try not to think of what happened before Big Bang because I don't think there is an answer for it. You know, there are certain theories. Some people think, oh, our universe is recurring, so maybe there was another universe which collapsed and so on. But at the moment, I don't think we know it, and you know, I like to base my thinking on what we actually know.
So the thing I always find weird as someone who isn't a cosmologist talking about it is that everything we know in space was in the Big Bang, but everything we know of time was as well. Time's just another dimension. So if space and time were created and had a genesis out of the Big Bang, the idea of before it doesn't have a meaning in terms of how we understand time as a thing. What that means is that it could be everything and nothing. We've just got no way of knowing in the framework of our current ideas and our current theories.
The origin of the universe is the one we understand the best. And this can seem paradoxical. People might think, well, isn't the universe, being everything, the hardest thing of all to explain? But from the point of view of physics, we have a pretty good framework for understanding how the universe can pop into being.
To my understanding, it's just sort of really dealing with time and space. And so the actual Big Bang moment, called the Big Bang Theory in a sense, that it suddenly expanded in space and time. It wasn't an explosion, because an explosion requires a difference in pressure. It was just this sudden expansion of space and time in a linear fashion. In some way, as far as we know, at least time in a linear fashion. Space is actually increasing at an accelerated rate now, apparently. So before that, who knows?
That's effectively a point before time existed and the universe as we know it existed. And since everything that we can record happened after the Big Bang, asking what happened before the Big Bang is kind of meaningless to me. It's kind of one of those odd questions where it's an interesting thought experiment, but it has no real value because we can't test it or probe it. So anything and everything basically is the answer is what happened before the Big Bang.
I can give you alternatives. One is that time itself began with the Big Bang. Another possibility is that the present expansion will finish and turn round and we will go into a big crunch, perhaps even into a big bounce. So there will be another Big Bang, another expanding universe. We could be just one expansion of a whole sequence of them. However, the limited amount of data we have suggests that that won't happen, that the expansion will continue forever. But as I say, it's all speculation that time began with the Big Bang, so there was nothing before it.
At the moment, we can sort of push our understanding of the universe to very early times, like 10 to minus 40 something seconds, where we actually understand a bit of physics about it. But beyond that time, we really cannot say much. And this is like, you know, working with black holes. You just can't get to that singularity in the black holes, and you can, yeah, that's a good time for, you know, for coffee or just discussion with wine. Yeah, oh, what could happen? But you know, it's like talking about anything like religion. you just don't have tools to answer this question, and yes, and you know, we can hypothesize multiverse theory, a lot of different things.
What about the universe from something? Suppose there was something there before. Well, a popular idea at the moment, it's been around for about 20 years, is that the Big Bang, what we call the Big Bang, is the origin of our universe, but not the entire physical thing. It's that it's one of many bangs scattered throughout space and time, and the assemblage of all of these things is truly eternal, has no beginning and no end. And so within that overall framework, universes like ours can pop into existence by some quantum tunneling process or something, and away they go, and they have their life cycle of birth, evolution, and maybe death, and we're just one instance of that. Now, you might think, well, that solved the problem of what happened before the Big Bang. Of course, it hasn't solved the problem of physical existence, because there still have to be laws of physics in this wider multiverse, this overall superstructure. And one could ask, well, where did those laws come from? And was there a beginning, an ultimate beginning, to this whole assemblage of things? And if there was, then we're right back to the same problem as we had before. So we're sort of moving the bump in the carpet here, and yet, so long as we have fixed, immutable laws, it seems to me that there's no other way of getting around the problem.
If it becomes sort of traceable in that regard, that suddenly everything and anything was possible. And if you've got an infinite amount of space, anything is possible inside that. So you get repetitions, and this is the whole sort of parallel universes theory that some cosmologists put out, that although our universe is bound and finite, it has a size, there's no discernible edge to it. There's probably material of similar properties beyond that we just can't see because it's outside of what's called our light cone, I think it is, that the light from those the bits and pieces outside of our light cone will never reach us, therefore we'll never be able to see that they're there, because the speed of light is finite. So it could be equivalent carbon copies of ourselves doing slightly different things, doing the same thing. Then suddenly we become a lot less special, a lot less unique, and possibly even a lot less interesting in terms of being part of the universe. I mean, we like to think of ourselves as special, but if we're just a natural outcome and we just happen to be a part of every universe almost in some way, something like us is, then yeah, suddenly it's a bit sad, really.
Well, as I say, that's one scenario. Another is that time and space are just 4 dimensions out of 11, and that collisions took place between membranes in higher dimensions and kicked everything off. But again, there's no data. There's nothing to test it with. Yeah? It's all speculation.
Comes in the idea of the multi-universes thing, that you might have all these universes coalescing with one another, and then suddenly they find this path that seems to work, and they're projecting out from that. Maybe. I don't know. Again, it's all speculation because we have no probe to actually analyze what happened before, because the globe, the cosmic microwave background, is hindering really us, what allows us to see the Big Bang moment. And then there's the actual Big Bang moment, which is obscured by this very sort of thick sort of background, where we believe that's when the first matter produced the first light, and in a coherent sense that we can actually understand for ourselves. And we see this everywhere, of course, and we only see the observable universe. So if I look that way, I'll see it. If I look behind me, I'll see it. If I look that way, etc. It's all around us. So we're looking in some sort of bubble in respect to the universe. So it's only the observable universe. What lies outside of that? Well, again, we don't know.
Trying to find an analogy for why. Imagine that you were flat, that you were two-dimensional, and you were moving around on the surface of a sphere. You've blown a balloon up, you've drawn a man on the balloon, and that man's moving around. How can that man on the balloon perceive the third dimension towards the interior of the balloon or the exterior of the balloon? They can't, because they can only move along the surface of the balloon. Now, they'd learned something about it by the fact that if they go as far as they can in one direction, they come back to where they started. So that gives them some idea that the space that they're on is curved, which is kind of what we do a bit with the universe anyway. That's how we understand the shape of the universe. So it's even more than that, but that's a good place to start visualizing it, is that you can be in a situation where there are things beyond your perception that you just cannot measure, you can't control. If you tried to get that person to imagine something totally a different balloon somewhere else, that's beyond their imagination, well, it's not beyond their imagination, but it's beyond what they can measure, beyond what they can see, because they've got no way in their two-dimensional surface of the balloon of getting off that surface and going elsewhere.
Because I think that's what you need when it comes to cosmology, because you need this outside-of-the-box thinking in order to understand what's happening to the universe as a whole.
The name of the game changes quite dramatically, however, if you don't regard the laws as absolute, universal, infinitely precise, transcendent mathematical relationships, but you regard them as something that can evolve and change and be part of this package. And then you're in with the chance of trying to explain the universe, or a multiverse if you prefer, in terms of co-evolving laws and states in a way that there's a feedback from the one to the other. And in particular, you have to have feedback through time, otherwise you can't explain in a self-consistent way. So my dream is that one day we'll be able to explain the universe in terms of laws that themselves are explained by the universe in a sort of loop, and that this loop will stretch into the past and stretch into the future, and that the reason the universe is as it is will have to do with this two-way arrow of time connecting principle. No, it's not causation. Nothing we do now can change the past, or alter the past, or even signal the past. But what we do now, we know connects with the past. We know this from the foundations of quantum mechanics. We know, Einstein called it spooky action at a distance, because it referred to what's going on here and here simultaneously being connected, but a change of reference frame means that this is in the past of that, and it's still connected. So we know that quantum physics connects the present with the past, but it can't be used to change the past or signal the past.
That's another big question, which I don't think anybody's got a good answer, although see, one thing which is interesting, it's the arrow of time. So why do we have the arrow of time? And I think I'm closer to understanding this concept than the time itself, because I think the arrow of time is related really to entropy. So, you know, the entropy which pretty much increases, and that somehow defines the way how we perceive time flow.
Well, without time, nothing happens.
If the fine structure constant, alpha, should change with time, depending a bit on how you define your units and things, you can see this as like the electric charge changing with time. And then I worried some years ago about if you had a maximally charged black hole and the electric charge were to change, would you violate cosmic censorship? That is, would the black hole disappear, and would you have a naked singularity, or would it violate the generalized second law of thermodynamics and reduce the horizon area? And there are all sorts of spin-off questions of that sort that would be opened up if it turned out even microscopically, a tiny amount, if the fine structure constant should vary. So that's my main interest in it. Of course, not just fine structure constant, but all of the fundamental constants of physics, because we want to know, is there a final theory that would produce these constants as part of the theory's output? Are these numbers, like the fine structure constant, just arbitrary, or are they connected to a body of mathematics that nobody has yet put together? It's always been my dream of deriving the fine structure constant, which famously has this value close to 1 over 137, deriving it from some fundamental theory. And I tried to do that many times over my career. I've returned to that, thinking, well, you know, sometimes I think, is there a nifty mathematical formula that would crank that out? So even though you didn't have a theory, you'd have a formula. Well, nobody's found one yet.
going beyond, so trying to go back beyond that is effectively completely unconstrained, because as soon as your ability to measure and model what happens breaks down, the possibilities also effectively, I think, break down. And so saying, how do you track back to the point of origin, to the singularity at the start of the universe, okay, we can get that far, or very close to it, but going back beyond that then effectively becomes, I think, becomes meaningless, at least from my view, because before that, anything and everything could have happened, but the point is everything effectively got reset at the point of Big Bang. The point when the Big Bang kicked off, everything got reset, and the universe as we know it came into being. And therefore, what happened before that is both untraceable and, in some degree, it sounds slightly arrogant, but also irrelevant, I think, because I don't think has had much impact on the universe as we observe it around. It's not terribly relevant to what we see and what we do and how the universe evolved, and therefore what happened before the Big Bang is kind of an interesting open question, but it gets more into the kind of speculative, slightly softer side of things in terms of astrophysics rather than dealing with observables and testables, which is what I like.
We've just got no way of knowing, in the framework of our current ideas and our current theories. Doesn't stop people speculating, but it's where you move from being science to science fiction to being just fiction. At the moment, we've no way of testing it, no way of finding out, no measurements that we can think of to make. So you could come up with any idea or any hypothesis, and it will be equally valid at the minute. No way of testing it, so it wouldn't be a scientific idea, but it's not something we can really approach and understand with our current way of thinking.
If we don't have the instrument to actually probe that particular idea, then what's the point of actually doing it, studying it at all? But you need people like that. I mean, take, for example, probably the most famous scientist of all time is Albert Einstein. He dreamed up this model of theory of relativity. At the time, we couldn't really confirm certain things. There was things that came out, like sort of the bending of light around warped objects, and such even a sun, because you need a total solar eclipse to see the warpage, if that's even a word, but sort of seeing the observed starlight with and without the sun, and actually there is a discrepancy of about 1.75 arc seconds, and that was actually predicted by Einstein. So as soon as that evidence came on board, Arthur Eddington from England at the time actually vindicated sort of Einstein's ideas at the time, and that just blew out. As soon as we had the evidence to confirm this radical idea, then people start taking notice.
No, I think I've because you're asking about responsibility of cosmology to answer these philosophical questions, yeah, and I don't think cosmology has that responsibility, but cosmology is supposed to study universe as a whole, and I think at certain stages it was all limited to observable universe, and fair enough, that's what we can study. I mean, when you start to talk about something which we can observe, which we've got some theories about, then you start to merge both of these sort of areas. You merge philosophy with actual cosmology, science we can do, but otherwise I think, you know, it's yeah, these areas really sort of overlap a little bit. Yeah. You go from being special and unique and interesting, and suddenly like, well, we're just part of the thin veneer on top of dark matter and dark energy again. It's like, it's slightly sad in that respect, but you know, it's in that regard, yeah, it would be slightly depressing, but at the same time, it would also be very interesting, because if you can look at that and go, look, these things are repeatable, and there's clearly a periodic mechanism, perhaps even, that traces the evolution of a universe, or of universes, then suddenly it becomes a lot more interesting, because we're highly unlikely to be the first time this has happened. So if it's periodic, it's like, well, how many times has it gone before? Can you test that? Can you see? Can you put in variations? Can you affect the universe? I mean, it's highly unlikely, and it's on scales way bigger than that of human reason, but certainly it's of interest that suddenly, is it possible to sort of look at these questions from not just a
personal perspective inside the universe, but actually look at it from a universe perspective inside a multiverse. And that suddenly becomes a lot more interesting and starts to drift towards philosophy, but it suddenly becomes a lot bigger and a lot more interesting in terms of the space you have to deal with as an astronomer and as a scientist.
So we live in this infinitely complex universe. We're not infinitely complex, so we make stories to explain it, we come up with hypotheses, we test them. And that's how we advance our knowledge and our understanding. In the current framework of what we understand, what we can perceive, we've got no way of doing that, but that's based on our current understanding, that's based on the current techniques we have, the technologies we have. At 50 years' time, the world will be entirely, utterly different. Not in terms of the physicality of what is, but in terms of our understanding will have increased leaps and bounds. The technology we have to analyse things will have increased leaps and bounds. And there will be new vistas opened up by that new technology. And it'd be very foolish to limit what I think that we could do in the future. So if you think going back 200 years, people were saying you could never have heavier than air flight. 100 years ago, they just started doing it. 50 years ago, we had people walking on the moon. It's amazing how quickly things move on, and if you try and predict that kind of development, it's almost impossible. The only thing that you can guarantee that you can predict correctly is that you'll be wrong in the predictions you make, and even then, you're rolling the dice on it. So we might be able to work it out. It may be that the models we have for how the universe came into being and developed that we have now change as we discover more with the next generation of telescopes, with the next generation of experiments at the Large Hadron Collider, things like this, and that gives an insight closer to the Big Bang itself and may even start shedding light on if there was a before, what came before. But that's beyond what we can say at the minute.
And if everyone agrees on how you conducted the experiment was appropriate and valid, if I use the term that now they use in Year 12 HSC syllabus, validity of the experiment, then people will actually start listening up. Because once the evidence there is plain and everyone agrees on the evidence, saying favours one model over another, or favours one theory over another, then we can actually move forward. And that's essentially what science is. Really is to disprove models and to favour others. And nothing in science is actually fully 100% proven. In fact, I don't like the word proof in a sense, because it's just giving the wrong impression of what scientists do. They actually want to confirm ideas and theories rather than saying, yes, it's 100%. It's got to be fluid. And that's what I like about science, is because we are limited in our sort of ability to take measurements, but we're not limited in the ability to imagine what's actually out there, of course.
Although science has defined our universe, from the Big Bang to the present with a confident analysis of the future, questions continue to evolve with our discoveries, leading us deeper into an alien reality far from the world we know. What caused the Big Bang? Was there a beginning? Is there an infinite amount of space, and if so, an infinite amount of possibilities? The journey to understand the complex and extreme circumstances of the Big Bang is an amazing accomplishment and perhaps the greatest intellectual human achievement to date. And one can only imagine what cosmological discoveries the future may hold.
Planet Earth, hundreds of millions of years in the future. Intergalactic explorers return to their home planet in search of signs of ancient civilizations. They find a planet that has changed beyond recognition. Gone are the familiar continents that we know today. Instead, they find a giant landmass with huge mountain ranges, massive frozen snowfields, and glaciers. The once thriving metropolis they seek has disappeared. A few broken remnants are all that remain, crushed and buried beneath tons of rock. Could this be a future vision of Earth? Naked Science asks, what forces could create such a bleak and barren world? And investigates how the awesome power of colliding continents shapes and reshapes our planet in an endless cycle of construction and destruction. Our world, the Earth. From space, it's easy to see the distinctive pattern of land that makes up the continents: North America, South America, Africa, Antarctica, Europe, Asia, and Australia. Giant landmasses separated by oceans that stabilize the environment with hospitable weather patterns, suitable for civilization and cities to evolve and prosper. Now imagine our planet ravaged by storm force winds, subjected to extremes of temperature, giant freezes, heat waves, and droughts. A world where cities are crushed and destroyed, where Africa tramples New York underfoot, and London freezes at the North Pole.
The geological future of New York is going to be rather traumatic. North America and Europe are going to collide with one another.
The world as we know it will be unrecognizable. This is not a portrait of the Earth after a devastating global disaster. This is how nature will shape our planet many millions of years in the future. This incredible remodeling is just part of a natural cycle that has shaped the Earth for the last 4 billion years, and will continue to do so until the sun finally destroys its surface once and for all. Today, our continents may seem solid, safe, and forever fixed in place, but they are none of those things. These great landmasses are constantly on the move. Speed up the last few billion years, and one can see the continents sailing across the globe. Powerful forces deep within the planet rip the continents apart and then smash them together in an ever-changing cycle of death and rebirth. Oceans disappear, mountains crumble, and rise again. Landmasses form and reform. Colliding continents are the mightiest force on Earth.
When we look at the history of planet Earth, we see that it is full of change. Change is part of nature, and this change continues today and will continue into the future.
To understand how the continents shape our world, we must first travel back in time to the very birth of the Earth. 4.5 billion years ago, the Earth is created from the debris left over from the formation of the Sun. Dust and debris collide and clump together. Once these clumps grow into objects about half a mile in diameter, they create enough gravity to attract more material. Slowly, these clumps grow into as many as 20 planets. As these new planets orbit the Sun, they begin to collide. One collision with the planet Theia, which creates the Moon, obliterates the surface of the Earth. The energy from the collision makes the Earth incredibly hot. At around 11,000 degrees Fahrenheit, it's more than 7 times hotter than the inside of a cremation furnace. Earth is a massive molten ball of boiling lava. This is primeval hell, where thousands of asteroids and comets bombard our world. But deep within the planet, a process starts that will lead to the first land. The heaviest elements, lead and nickel, sink down toward the center of the Earth to form a molten core. The lighter elements, including oxygen and silicon, rise toward the surface, where they erupt in volcanoes of molten rock. Slowly, the Earth's surface cools. Molten lava solidifies to form patches of crust, the seeds of the first continents. But even as the first land is born, it faces a battle to survive.
We were being bombarded by a large number of asteroids very early in the history of the planet. So there's a lot of dynamic change from being walloped by giant impacts, disturbing things.
Geology professor Sam Bowring is an expert in early Earth and the genesis of the continents.
When we had an early crust is an interesting question. I suspect we had an early crust from day one. The question is, how long was that preserved? When the Earth was being bombarded constantly by asteroids, the chance of preserving any small chunk of that crust was very low.
The relentless bombardment destroys the new planet's crust almost as soon as it forms. This recycling of the surface continues for many millions of years.
But as the flux of asteroids began to wane, and as the Earth matured a little bit, I suspect the early crust lasted a little bit longer.
Eventually, the barrage from asteroid impact slows down. The surface of the Earth continues to cool. But the Earth is missing one vital ingredient: oceans.
Where Earth got its water has been a controversial topic over the years. I think most people now think that many meteoritic bodies actually contain quite a lot of water.
Water carried by meteors and asteroids may form the oceans that surround the first continents. The Earth, 4.4 billion years ago. Our planet is now 150 million years old, and the first primitive landmasses have formed. They are not like the 7 instantly recognizable continents of today. They are just small rafts of rock floating on the mantle. But now a type of rock appears on the Earth's surface that will form the nucleus of future continents. A rock buoyant enough not to sink into the bowels of the Earth. Granite. In South Africa, in the Kaapvaal region southwest of Johannesburg, geologists examine ancient granite that has survived the ravages of time. These are the ancient remains of what some people consider to be the first true continent.
We're looking at the relics, the remnants of the first continental nuclei. This is one of the oldest, but certainly the best preserved continental nucleus in the world.
Geologist Alex Kisters studies how granite formed the first continents.
The rocks here are so important because they are remarkably well preserved, much better than anywhere on Earth. And that allows us actually to study processes that were involved in the formation of these early crustal rocks.
Kisters is collecting samples to date the age of the granite.
We're drilling these little rock cores, taking them out, and then sending off that later onto the lab to be dated.
Dating rocks is a complex process because over long periods of time, the minerals can break down and reform into new rocks. Scientists look for an ingredient of rock that is tough enough to withstand the test of time. The answer is zircon, a crystal that is made inside molten rock as it solidifies. Even if the rock is destroyed, the zircons are durable enough to survive.
Zircon is an incredibly interesting mineral, and it incorporates uranium and excludes lead, and that sets us up to have basically nature's time capsule.
To illustrate this process, Imagine that this hourglass is a newly formed zircon crystal. Sand in the top represents uranium. The sand in the bottom represents lead. Over millions of years, the uranium in the zircon turns into lead. Measuring the relative proportions of sand in the top and bottom of the glass reveals how much time has passed. Uranium's relentless decay into lead gives us a natural clock. Using this technique, geologists date this granite at 3.5 billion years old. This makes it some of the oldest rock on the planet. These rocks make up a major part of what is known as the Kopval Craton. A craton is an ancient raft of rock, light enough to float on the mantle, and around which a continent will grow. Ancient cratons have also been found in the heart of the Australian and North American continents. The craton here in Kopval in South Africa stretches for 463,000 square miles. It's almost twice the size of Texas. Without granite, the craton and modern continental crust wouldn't exist. Granite forms when minerals in the crust melt, then react with water, cool, and crystallize. Because it is made of lighter minerals, granite is less dense than other rock in the mantle, so it floats on the surface and mixes with other rocks to form rafts of land. The Kopval Craton is not totally built from granite. The oldest rocks here are these amazing pillow lavas exposed along the Komati River. 3.5 billion years ago, they form under the sea as lava emerges from an underwater volcanic vent. Upon contact with water, the lava immediately gains a solid crust, which then cracks and oozes additional large blobs called pillows.
These rocks are amongst the oldest that we know. It's basically identical to pillow lavas that we see on a recent ocean floor or in settings like Hawaii.
The Komati pillow lavas begin their life on the ocean floor, but are pushed up out of the sea to form part of a continent. But where did the granite come from? To create it, you need the right mix of minerals. A new theory suggests that life itself may have provided the missing ingredients. It may sound like an outlandish idea, but there's some evidence that living organisms that use photosynthesis appeared around the same time that the continents began to grow, 3.8 billion years ago. Scientists suggest that early organisms, microbes, helped speed up the breakdown of rock emerging at the Earth's crust. Over hundreds of thousands of years, this rock breaks down into new minerals, which sink back into the mantle. Deep below the surface, they heat up and form granitic magma. The magma rises into the protocontinent, freezes, and forms huge solid rafts of granite. Now stabilized, the craton begins to grow, forming new baby continents. But cratons are not the only factors at work. More powerful forces are building up deep within the planet. Forces that have the power to rip apart landmasses and smash them together, changing the face of the planet forever. Four and a half billion years ago, the Earth forms. For many years, it is bombarded by asteroids and meteors. Slowly, the molten planet cools, and small landmasses form around cratons of granite rock. Massive forces from deep within the planet rip apart and smash these small protocontinents together as they grow into the large landmasses we see today. The surface of the Earth, the crust, is made up of a giant jigsaw of interlocking pieces called tectonic plates. The separate plates themselves sit on the mantle, the layer between the crust and the Earth's core. Although the mantle is made of rock, the heat and pressure deep down mean it's flexible enough to allow the plates above to move up to several inches a year. Evidence for the theory of continental drift was first proposed in 1912 by German scientist Alfred Wegener. He noticed that identical fossils were discovered oceans away from each other. Paleontologist Professor Mark McMenamin of Mount Holyoke College in Massachusetts is an expert in fossil records.
Wegener noted that a freshwater organism cannot cross a salty sea. And so if you find the fossils of a freshwater organism or a land creature on two continents that are now greatly separated by distance, they must once have been closer together.
By identifying like fossils on different continents, scientists can map which continents were joined in the past.
The fossil distributions will tell us where fossils occur and how the continents must have been juxtaposed. Fossils that are identical but occurring in very different parts of the world imply that the continents have drifted.
When he first proposed his theory of continental drift, Wegener was laughed at. The idea that continents could actually move was considered preposterous. The problem was, he didn't know how the continents moved. The missing mechanism wasn't discovered until the 1960s. Plate tectonics is powered by heat.
Plate tectonics is being largely driven by the fact that the interior of the Earth is much hotter than the surface.
The temperature at the center of the core is 10,000 degrees Fahrenheit. It's as hot as the outer parts of the sun. Much of the heat is left over from the collisions and massive bombardment during the early days of the Earth. The rest comes from radioactive decay of heavy elements in the core. Heat escaping from the core creates convection currents in the next layer of the Earth, the mantle. The process is like a lava lamp, where heat from the bulb at the bottom creates convection currents in the oil, pushing the synthetic lava upward. The heat melts part of the mantle and sends plumes of magma, molten rock, rising to the surface. It rises between cracks in the plates, creating new rock that pushes the plates apart.
I think that plate tectonics is virtually inescapable on this planet. It's an exceedingly efficient way to cool the interior of the Earth.
This formation of new rock splits apart and separates the plates and the continents sitting on them. Today, the majority of this new rock forms under the sea, creating vast interconnected volcanic mountain ranges that extend through all the major oceans of the world. One range can clearly be seen at the bottom of the Atlantic Ocean, along the mid-Atlantic Ridge. It stretches more than 12,000 miles from the sub-Antarctic to the Arctic. It comes to the surface in a few places. Iceland was created from volcanic lava, bubbling up at the junction between the North American and Eurasian plates. It's one of the few places on Earth that one can actually see continents being pushed apart.
We are watching here geological structures that you cannot really watch anywhere else. It's like a big textbook of geology. This is where the Earth's crust is being made.
Pál Einarsson, professor of geophysics at the University of Iceland, monitors the mid-ocean ridge where the continental plates are splitting apart. The ridge in Iceland is almost 3 miles wide. On one side is the North American plate, on the other side, the Eurasian plate. The rift here grows as new rock forms at its center, pushing North America and Europe away from each other. The Atlantic Ocean widens, and the two continents drift apart. Eventually, the Atlantic could become as big as the Pacific. To measure how fast they're splitting, Einarsson takes global positioning system readings at specific points along the plate margin.
We put the antenna right on top of the point, and then we can calculate the exact position of this point in the world with respect to the center of the Earth.
Although the ridge appears calm and there's no magma rising to the surface, Einarsson's measurements show that the two continents are drifting apart by around an inch a year. So by the end of the century, Europe and America will be almost 8 feet further apart. The movement in Iceland is typical of the processes shaping the continents since their birth 4.4 billion years ago. It's part of the great cycle of the Earth's continents. The new crust, created at the mid-ocean ridge, moves away, cools, and eventually sinks back into the Earth. When the first proto-continents formed, there were several interconnecting tectonic plates, constantly bumping and grinding against each other, pushing the new land over the planet. Today, the Earth has over a dozen plates, some colliding together, some moving apart. They are powerful enough to move a continent the size of North America over 3,000 miles in 200 million years. That's 15 miles every million years. The Earth, 3.4 billion years ago, and plate tectonics pushes the proto-continents together. They combine to form ever larger tracts of land. Scientists suggest that cratons combine with other cratons to form a supercontinent, a huge continuous stretch of land. It's called Valbara. Scientists are unsure of its exact shape or size, as only a few pieces, like the craton in South Africa, still remain. But Valbara's days are numbered. A rising plume of heat is growing beneath it. It's about to rip the world's first supercontinent into pieces. $2.7 billion years ago, Valbara, the world's first supercontinent, still dominates the planet. But plate tectonics, powered by heat from the Earth's core, is about to split it apart. Rock is a good insulator. When a continent gets very large, the rock traps heat beneath it. As it gets hotter and hotter, a plume of superheated magma builds up beneath the giant continental mass. The temperature continues to rise, and pressure in the mantle increases. Eventually, the crust can no longer contain the pressure, and the hot lava breaks through, ripping the land apart. You can see this process happening today in Africa. Heat from the Earth's core is ripping the continent apart. A giant rift valley runs from the Red Sea down to Mozambique. Giant cracks are opening up in the land. Volcanoes, like Kilimanjaro, mark spots where molten rock have risen to the surface in the past. In 10 million years, the eastern half of the continent will have split away. The molten lava trapped beneath the giant supercontinent of Valbara eventually smashes through the surface rock. The continent ruptures into several smaller pieces. These bits of land sail across the Earth. But nobody knows what happens to them or what the planet looks like at this time. The Earth is entering the Dark Ages. It is over 2.5 billion years since it was formed. It will be over 1 billion years before another supercontinent forms. The Earth is entering a deadly cycle of destruction and rebirth.
The theory of continental drift suggests that we go through cyclic phases of continental dispersion and then continental collision. And the continents then seem to move apart from one another and then collide with one another over a maybe 100 million year or more time scale.
When a large continent splits apart, the separate pieces travel away from each other, pushed by the creation of new land at the ridge between plates. Because the Earth has a constant surface area, the same amount of land created must be absorbed into the Earth. This process happens at subduction zones at the junctions of plates. At a subduction zone, crust dives down into the mantle to be melted to form new rock. When the plate subducts into the Earth, it brings two pieces of land together. When they collide, a new supercontinent starts to form. It is now 1.1 billion years ago on our timeline, and the next known supercontinent has formed. Its name is Rodinia, and it holds almost all of the continental rock on the surface of the Earth. Still, no one knows exactly what it looked like, but at its heart is an area that will eventually become North America. 350 million years later, the cycle of annihilation and creation starts again as the buildup of heat beneath the surface of the Earth tears Rodinia apart. When Rodinia splits, it forms several smaller continents that for millions of years drift apart and then drift back together again to form Gondwana, a supercontinent in the southern hemisphere. Eventually, after several 100 million years, Gondwana slowly splits apart. Plate tectonics pushed the land back together to create the world's last supercontinent. It's a huge landmass known as Pangaea. All the continents we know today are here, joined together. Geologists are able to plot the continents' relative positions because 350 million years ago, there are numerous species on Earth, each living in distinct regions.
This specimen that I have right here is the first trilobite that was ever described from what is now the United States. It is exactly the same type of trilobite that occurs on the other side of the Atlantic Ocean in North Africa. So we know then that the trilobites in the old and new worlds must have been close together because they're so closely related.
The fossil records show that North America and Europe rest next to one another. The land where New York now sits is next to Morocco in North Africa. The Atlantic Ocean does not exist. The east coast of South America nestles against the western coast of Africa, while Australia, India, and Antarctica are joined to the southeast of Africa.
If we want to look at a picture of the world 250 million years ago, we're going to look at a world in which a four-footed creature could walk from one end of this landmass to the other.
Pangaea is one giant continuous landmass. It not only makes the world look very different, it also has a dramatic effect on climate. Because much of the land is located far from the sea, the climate of the interior changes radically from season to season. It gets very hot in the summertime and extremely cold in the winter.
You don't have the moderating influence of the ocean that we have today. So it's a very different world. And it's a world that in some ways is harsher and less hospitable, at least to life on land.
It's thought that the climate change caused by Pangaea's formation may have played a role in one of the largest mass extinctions on Earth. This event, known as the Permo-Triassic mass extinction, wipes out about 90% of all life on Earth.
It's been called the mother of all mass extinctions. I would consider that the formation of Pangaea, with its climate worsening effects, to be a contributing factor, however, and not the sole cause of the mass extinction.
250 million years ago, and the supercontinent of Pangaea is breaking up. The continents we know and recognize today begin to take shape. Over the next tens of millions of years, South America drifts away from Africa, North America away from Europe. Australia splits off from Antarctica and heads north to warmer climes. The positions of our continents are becoming familiar, although their distinguishable features are not. The world's vast mountain ranges, the Alps and Himalayas, and its great valleys, like the Grand Canyon, are yet to form. They will emerge out of one of the biggest battles in nature, the battle between colliding continents. Earth, 100 million years ago. The continental map of the modern world is gradually becoming recognizable. But a battle is still raging between the continents that will change the face of our world forever and create some of the most extraordinary geological features on the planet. As the continents move slowly across the Earth, crust and rock is dragged back down into the Earth at subduction zones between the tectonic plates. But when continents collide at the plate junctions, sometimes there is a battle for supremacy. If neither plate will submit and drop down to be consumed by the mantle, then both the continents slowly smash and grind into each other. These pinch points of continental collision build mountains. The Alps are the largest mountain range in Europe. Higher than the Rockies, the Alps stretch from France in the west through Italy, Switzerland, and Austria to Slovenia in the east. Their formation is a direct result of a continental collision between Africa and Europe. The story of the Alps begins when the African plate breaks away from the South American plate. It starts moving toward Europe.
Without the plate movement, there wouldn't be any mountain on this planet.
Professor Gerard Stamfli of Lausanne University in Switzerland studies the processes that built the Alps. The African and Eurasian plates start to move toward each other, trapping a third, smaller Iberian plate between them. The three plates collide. The Eurasian plate is pushed downward into the mantle, chopping off the Iberian plate. The Tethys Sea begins to close. As the Eurasian plate grinds underneath the African plate, it pushes the Tethys Sea floor and part of the Iberian plate 600 miles north and many thousands of feet into the air. Rocks that started life on the bottom of the ocean end up at the top of the Alps.
Quite fascinating to imagine that if you are on top of the Matterhorn, you're actually staying on top of Africa. For geologists, Africa stops in the Alps.
Over the next 100 million years, the continents continue to smash together. New mountain ranges start forming around the globe. The largest, the Himalayas, form as the Indian plate charges northward toward the Eurasian plate. It moves at 2 inches per year, lining up a head-on collision. The movement of the Indian plate leads to a clash between two giant continents and creates some of the highest structures ever to exist on Earth. The incredible power of continental drift not only builds mountains, it also sculpts one of the world's most recognizable landmarks, the Grand Canyon in Arizona.
The Grand Canyon is a great scar on the surface of the Earth.
Geologist Ron Blakey has been studying the canyon for over 30 years.
It's just a wonderful place to come face to face with planet Earth.
The Grand Canyon is 277 miles long and up to 18 miles wide. At its deepest, it stretches down for over a mile. The gorge exposes the interior of the North American continent. It's like looking through the pages of a book. Each layer tells a story about the past.
One of the really neat things about Grand Canyon is as we go up the walls of the Grand Canyon, it's just like going through a time machine.
Layer upon layer of rock reveal the geological history of North America, from present day to 2 billion years ago. The deeper you go, the older the rocks. By studying the layers, Blakey can piece together the history of the canyon. He finds some of the most interesting evidence at the very top. Fossils of ocean creatures.
Wow, this bed's the jackpot here. What we have is an extraordinary example of a Permian seafloor. The most important thing it tells us with respect to the Grand Canyon is that this area had to be near sea level when these rocks formed. Now it's 7,000 feet above sea level on the rim of the Grand Canyon. So something had to happen. Either the sea had to fall 7,000 feet, and we're pretty sure that didn't happen, or this landscape had to be uplifted 7,000 feet. We're pretty sure that happened.
250 million years ago, the canyon starts to form as a result of a collision between the Pacific and North American plates. They collide with such force, the North American plate thrusts more than 2 miles upward. What was once seabed rises over a period of 15 million years to form a vast plateau far above sea level. It stays that way for millions of years until it is transformed by water erosion. Six million years ago, several hundred miles south of the canyon, plate movements open up the Gulf of California to the sea. For the first time, small streams in the Rocky Mountains could empty into the ocean.
So if we're starting a stream at 14,000 feet in the Rocky Mountains and carving down to sea level, and the Grand Canyon just happens to be in the way, the Grand Canyon's going to get cut out.
These streams merge to form what is now called the Colorado River. It cuts down through the land, heading toward the Gulf of California.
It took a river to carve the canyon. The water has carved down through the rocks layer by layer by layer, removing material out of the canyon and leaving the great void that sits behind me.
The Grand Canyon is a testament to the awesome power of the continents in shaping our world. Back on our journey, tracing the birth and death of the continents, it is now 20 million years ago. 2,500 miles south of the Grand Canyon, another plate collision is about to take place. The map of the modern world is almost complete. At this time, water flowing freely between the Pacific and Atlantic Oceans still separates North and South America. Over many millions of years, the Pacific plate begins sliding under the Caribbean plate. The pressure causes underwater volcanoes to erupt. Some explode with such ferocity that they create a range of small islands between North and South America. Over the next 17 million years, ocean currents deposit sediment in gaps between these new islands. Gradually, the sediment builds up and compresses to form land bridges between the islands. 3 million years ago, the Isthmus of Panama, a narrow strip of land, finally joins North and South America. It separates the Pacific and Atlantic Oceans. The flow of water between the two stops, and ocean currents must take new routes. This causes yet another change in the climate of our planet. It changes the movement of warm seas around the globe, disrupting weather patterns, possibly pushing the planet into an ice age. Many species are wiped out. The continents as we know them today are formed, creating the nice, hospitable environment for human civilization to evolve and thrive on planet Earth. But how long will it last? The forces that power plate tectonics are still active and will tear our continents apart once again. They will build a new world, one that may trigger another mass extinction and push humanity to the brink of annihilation. A view from space reveals Earth's continents as we know them today. There are 7 in total, but some are separated by a political divide rather than a geographical one. Africa-Eurasia is a supercontinent comprising of Africa, Europe, and Asia. It stretches from the Siberian Plateau in Russia to the Cape of Good Hope in South Africa. A spectacular route across 3 continents, incorporating dramatic climate change, vivid scenery, and diverse cultures. However, Africa-Eurasia isn't the only supercontinent on the planet. Because the Panama Isthmus links North and South America together, they too can be thought of as one vast landmass. And if the Bering Strait between Russia and Alaska were to freeze over, it would be possible to walk from Cape Horn in South America to the Cape of Good Hope in South Africa. A journey of around 25,000 miles. But this won't always be possible, for powerful forces deep below the surface continue to send the continents hurtling across the globe. A process that started at their birth 4.4 billion years ago, and one which will continue long into their future.
What we're observing at the moment is only a snapshot of the Earth's global cycle that has been undergoing for the last 4.5 billion years probably, and will be undergoing, even if we're not around anymore.
The global continental cycle has another impact on our world. It causes many natural disasters. Plate movement creates stress points, which lead to volcanic eruptions. As continents split apart, instability at the plate junctions causes earthquakes that rip apart whole communities. This one, on October 8, 2005, in Pakistan-ruled Kashmir, killed nearly 75,000 people and left up to 3 million homeless. And when plates subduct into the earth, their death throes produce devastating waves. The 2004 Indonesian tsunami is just one demonstration of the terrifying power unleashed when plates move. Such natural disasters are part of the continental cycle, and they're not going to stop.
Plates moving is something we have to live with. There's nothing we can do about it. It's going to happen. There are going to be big earthquakes in California. There's going to be a lot of damage. There's going to be loss of life.
In recent years, it seems as though natural disasters, powered by the movement of the continents, have been on the rise. But what we are witnessing is an increase in awareness, rather than an increase in the number or severity of natural disasters.
I think what we're really seeing here is a very raised consciousness of the public. With instant communication abilities, much more publicity is given to volcanic eruptions and earthquakes.
We are observers to only a very short period of the life of the Earth. If we could monitor earthquakes and volcanic activity caused by plate movements over millions of years, we would see a very different picture.
When you look at something over 10 years, you might have 10 major earthquakes. The next 10 years you might not have any, but that's not significant. It just is related to the short period of time that you're making the observation at. When you start looking at hundreds, thousands, and millions of years, all that averages out.
It's impossible to predict exactly when the next disaster will occur. But it is possible to predict where it will happen. The plate boundaries. Map the location of earthquakes and volcanoes, and they line up with the cracks between plates. Plot where these plates will move over the next tens of millions of years, and the future looks bleak for many of the world's cities. So what will our world look like in the future? 50 million years from now, the Atlantic Ocean will widen, pushing New York further away from North Africa. Meanwhile, in the southern hemisphere, Australia will be on a collision course with Southeast Asia, and in Europe, Africa will head north, closing the Mediterranean Sea. A new mountain range will form where Italy and Greece once stood. Known as the Mediterranean Mountains, they will be as big as the Himalayas, extending from Spain across southern Europe, through the Middle East, and into Asia. 100 million years in the future, and the power of continental movements will render the surface of the Earth unrecognizable. The Atlantic Ocean will continue to widen, but a subduction zone will form along its western shoreline. The first sign of it can be seen today in the Caribbean, the Puerto Rico Trench. This trench will grow north and south along the east coast of North and South America. This vast subduction zone will consume the Atlantic Ocean, dragging Europe and Africa back toward the Americas. 250 million years in the future, intergalactic explorers returning to their home planet will find a world very different to the one in their records. There will no longer be 7 continents, but one gigantic landmass containing most of the land on Earth. They could find it a barren, frozen world. The explorers search for the remains of our cities, but when Europe and America collide, any cities along the coastlines will be gradually destroyed.
The geological future of New York is going to be rather traumatic. In the long term, New York is going to be at the site of a continental collision. North America and Europe are going to collide with one another and produce a distinctive suite of rocks which will eventually be crumpled between the two continents as they collide.
New York and its neighbors will be crushed and buried beneath the surface, leaving no more than a few remains.
In the future, geologists will be able to find remains of New York City trapped in the rocks themselves, either buildings or plastic bottles or old autos and their parts. All of these things will be incorporated into the fossil record and will be recognizable to a future geologist who knows what she or he is looking for.
Because of its similarities to past supercontinents, this future landmass is called Pangaea Ultima, the final Pangaea. Nearly all the landmasses in the world will be joined together. Pangaea Ultima will probably experience climate extremes, freezing winters and scorching summers. This deadly weather could have devastating effects on all life on Earth.
The implications for the human race are interesting to speculate about. Certainly, the disposition of the continents over time will affect Earth's climate, and that will in turn have an influence on which organisms survive, which go extinct, and could be a factor in future mass extinctions.
The world we know is inching slowly toward its own destruction.
The processes that shape the surface of the Earth are never going to change. We're going to have earthquakes, we're going to have volcanoes, we're going to have tsunamis and hurricanes, regardless of whether humans inhabit the planet. And so the planet will always be here, probably. Plate tectonics will operate for the foreseeable few 100 million years. The question is whether humans will be here to witness it or not.
But even Pangaea Ultima might not be the end of the story. The forces that created it may eventually rip it apart and start the cycle of death and rebirth again. But by then, the impact of colliding continents could have been too much for our species. With our cities destroyed and the climate severe, we may have already left our planet in search of a safer home.